Welcome everybody in TUKE Space Forum. We have here also our guest Bernhard Schulz. Today it will be about very special experiment, very special physical observatory, SOFIA. And let me introduce. It's my honor to introduce the Bernhard Schulz. Bernhard, our speaker today. Bernhard Schulz is German astrophysicist with strong record in space-based infrared instrumentation. His scientific instruments include active galactic nucleus, ultraluminous galaxies, dust, and the interstellar medium, but also small solar bodies. He received his PhD in 1993 in astronomy from Ruprecht Karl University in Heidelberg at the Max Planck Institute for Astronomy, and then went on work at the European Space Agency. The first in Netherlands, then in Spain, as calibration scientist and deputy instrument team lead for ISOP-HOT, which is one of the four instruments of the Infrared Space Observatory. Then in 2002, he joined Caltech in Pasadena, California, to help set up the NASA Herschel Space Science Center at IPEC as team lead and instrument specialist for SPIRE. His time at Caltech also include contribution to the Spitzer Space Observatory. And then finally in 2018, Bernhard Schulz was appointed Deputy Science Mission Operation Director for SOFIA by the University of Stuttgart in Germany, with duty station at NASA Ames in Moffett Field in California. And his role his roles as selection official for the German science program on SOFIA. And also as quasi-ambassador between both countries. So this is our today's speaker, and he will speak about the infrared observatory flying on board the Boeing 747 SOFIA. So Bernhard, please, we are waiting for your presentation. I will stop sharing my screen. You could share your presentation.
Okay, well, good afternoon. It's morning here in California, I hope I'm awake enough now. Had a coffee. Okay, let's see if you can see all this here. Could you just give me feedback if you see fine?
Yes, we could see it. It's perfect.
Yeah, perfect. Okay.
Yes, perfect.
Very good. Okay, so yeah, I'm going to tell you a little bit about quite a special type of observatory that you don't find anywhere else. Normally what you do with the telescope, you put it onto a mountain, you connect it to the bedrock, you try to make it as vibration-free as possible, and because the details that you're observing are very small, and so you really want this rock solid and steady. But you know, who thinks of putting a telescope on something wobbly and shaky like an airplane? But this is exactly what we have done, and I'm going to tell you everything about it that fits into the time that we have. And well, let's get to a start. I'm the Deputy Director of Science Mission Operations of SOFIA. That means I work with the team that does the planning for the science operations. So it basically, we in the end decide what we are going to observe with this observatory. And of course, this is done with a lot of input from scientists, from our science community, and so forth. Okay, and I am so SOFIA is an 80-20% partnership between the US and Germany, and I am the German representative on the science of that's done with SOFIA. So my home institute is actually the University of Stuttgart. Okay, now what we're going to talk about is, first of all, I think I will need to give some introduction into the infrared and why do we care, what is interesting about it. Then I'm going to describe the observatory, give you a set of science examples that we have done, and talk about the instrumentation and the capabilities. And finally, we come also to actually how is the observing done with SOFIA in practical terms. In particular, also, if you are scientists yourself and you want to write proposals for SOFIA data. Okay. By the way, so if you have questions, I think it's no problem if you interrupt, but we will need to stick to the time somehow. I have a lot to show. If things don't get shown, you have the presentation available, I suppose, so we can then also do it this way. Okay, so radiant heat. That's what is also another name for infrared. It is in the electromagnetic spectrum, it is situated between the visible light and the microwave and radio spectrum. It actually covers, compared to the light, which is just this tiny part here, the infrared is quite a large wavelength range. It has been described already since the 1800s in the literature. It was known that it could be reflected using mirror. William Herschel showed that it is a part of the solar spectrum. That's his famous experiment with the thermometers, where he showed that even beyond the edge of the solar spectrum, he could still see a rise in temperature. Now, this is called infrared light now. These are basically longer wavelengths of than visible light. Now I have to see, here. So why is infrared interesting? Well, it has a few interesting properties. First of all, it is transparent. So the dust is transparent to infrared light. That means we can basically see through dust. The other property is, even though dust in space in particular is quite cold, it can still be seen in the infrared, especially at the longer wavelengths. So it effectively re-radiates. Everybody of us radiates infrared radiation because we all have a certain temperature. The higher the temperature, the more infrared radiation gets emitted. And this is, for instance, used by these infrared thermometers that are nowadays used for instance, the coronavirus detection. And well, then, because the infrared light is a little bit, so the photons have a little bit lower energy than visible light. There's a number of other diagnostics that are available there, in particular lower energy transitions, vibrational and rotational, of molecules that you can observe in the infrared. And well, there's one more thing that is also interesting. If you have line dust grains, then they can polarize continuum emission, and you can measure, of course, also the polarization degree of infrared. And that gives you then ideas about the magnetic field that typically aligns such grains. So how do we do this? Infrared broadband photometry and imaging is one way of doing this detection of infrared. We can find out about the temperature, and from that we get optical depth of the material that we see. Typically it's dust in the interstellar medium, dust grain sizes, mass, etc. So we learn about dust masses that are, for instance, in galaxies, and that gives us ideas about star formation and so forth, and also how much enshrouded this galaxy is. And then, of course, if we go into infrared spectroscopy, which, you know, you can also characterize it as a more subtle photometry, because now you're basically having much finer filters. Then you can really drill down to the constituents of gas and dust, you see the lines, and you actually can find out about the physics that is going on in the observed region. The bread and butter of SOFIA, if I want to tell this in very basic terms, is star formation. So SOFIA has all the wavelengths at its fingertips that are necessary in order to study these very fundamental things like, you know, how do stars form? How do solar systems form? Effectively also, how do planets form then? And what was before that? So here's a picture of that actually Herschel took, a space observatory for the mid and far infrared. And you see all these filaments, and the colors give you some idea about temperature in those regions. And all of this is visible and accessible to SOFIA and to any other infrared observatory. The problem is there are none, and let's talk about that a little bit. Before we do that, however, I want just to make another case for the infrared in general. So there are several components that are in the electromagnetic spectrum. I have to move this away here. Okay, very good, because I don't see much of it on my screen at the moment. I see the pictures. Okay, so the cosmic microwave background is pretty much the coldest radiation that we get from space. And that originated shortly after the Big Bang. And when we had the, and then we have the cosmic optical background that developed after that. And that is mainly from radiation of stars and black holes. So that populates the short wavelength spectrum. Okay, and then we have the cosmic infrared background, which effectively is re-radiated optical radiation by dust. So the dust is heated, and then the dust re-radiates that energy in the infrared, and that's the cosmic infrared background. Okay, so in energetic terms, the CIB is about half of the energy that is in the that was in the optical radiation. So it is a major component of the energy that's in the universe. All right, so after I hopefully have made your or raised your interest in the infrared, let's see how we can get to it. And well, this is the diagram that shows you what the issue is here. It is our atmosphere. So usually is a good thing. We can breathe and everything, but for infrared astronomers it's a particularly bad thing because it blocks our view to most of the infrared spectrum. And so for the astronomers, it's really an issue. Okay. So what is blocking the infrared is water, water vapor in the atmosphere, and some other molecules. And the only way basically to go and observe the infrared then is either from a very high mountain, and even there we have still a lot of atmosphere, so also there we can only see through the famous infrared windows at 10 and 20 microns, but everything else is still blocked. And the next possibility is, of course, an airplane or a balloon. And the only way to completely get rid of any of the absorption of the atmosphere is to go to space. but that of course is quite expensive. So here we have the solutions: airplanes, balloons, and spacecraft. Okay. They all have their goods and bads, and I'm going to talk about, of course, the airplane solution today, and that has a particular interesting part. It is good for instrument development because we always land again, and so you can take out your screwdriver and work it out if something fails. Of course, there's still a residual atmosphere, and you have to deal with that, and there are various ways to do this. So here's the solution to the troubles in that respect. SOFIA is a modified 747 SP aircraft with a 2.7 meter telescope built into it. It's a joint program between the US and Germany. US pays 80%, Germany pays 20% of the dues. And it gives on a regular basis access to the far infrared spectrum. So basically everything between even visible and the far infrared to sub-millimeters is available there. SOFIA flies up to almost 14 kilometers, above 99.9% of the water vapor in the atmosphere. However, even that tiny little residual water vapor still gives us some trouble, and we need to work around that sometimes. It has a suite of infrared imagers, spectrometers, and polarimeters, and it's operated by NASA and DLR. And the actual actors in this game is USRA and DSI. So USRA, they are basically a contractor for NASA, and DSI is a partner to DLR, who actually do the day-to-day work. And yeah, the regular science operations began in 2014. And SOFIA has a design lifetime of 20 years. And yeah, there's always some discussion about how long it should operate, but we think it should operate at least those 20 years because it is quite a unique facility and it does cutting edge science. So how does it look? This is a cutout here, and what you see is this is the main cabin here. So all of this front part here is pressurized because we're flying quite high. The modification of the aircraft was the pressure bulkhead here, which then you know, is also the carrier, the mount basically for the telescope. So you see the telescope here, it's kind of like a scale. So there's a counterweight here on this side where the instrument is mounted, the science instrument, so either camera or spectrometer or so. And on this side here we have a telescope, and so there's the primary mirror, the secondary, and eventually there's a third mirror down here which reflects the light beam into this canal here through a window, and then it goes into the science instrument and can be analyzed. This part here is under ambient conditions. So once we're in the stratosphere, the pressure here is very low. There's a big door that can be opened. And that was one of the things that was quite difficult because people had to, you know, engineers had to go and find out what is the best way to do this in order to have a nice laminar airstream around that door so that it doesn't get caught inside and potentially rips off tail. So in the pressurized area here, we have various consoles. Inside it looks like Star Trek almost. So you have the mission operations station here. So the mission directors sit here. The instrument controllers sit here. these are the telescope controllers on that side. And then scientists are having various places where they bring their own laptops often and already pre-analyze the data. And then we also have an educator outreach console. So we have teachers flying with us who then, who learn everything about this observatory, and then they tell their pupils again about their experience. So here are some real pictures how this looks, and as I said, it looks pretty much like Star Trek in a way. So this here is the view towards the rear of the aircraft. So it's pretty funny when you take off in the aircraft, you do this actually with your back to the front, because the interesting action is actually towards the back. This is where the telescope is mounted. So what we see here is the bulkhead, the blue, everything that's in blue belongs to the telescope. On the left here, this console, these are the telescope operators. On the right, this console here is mission directors, and behind that there's the instrument controllers. Here we see the console of the instrument controllers, and this Jürgen Stutzky here standing there and overseeing this all. Yeah, and then the telescope operators, I said, they're on the left side. This is the console. And then here you have this area with the scientists who already have a first look at their data. Yeah, and then of course here, this is the cockpit of the pilots. I took this on one of the flights in New Zealand, where there was beautiful aurora. And of course in the south, you call this aurora australis. And the pilots had also fun, and they were even then willing to pose with the aurora there. And yeah, the pilot's job is pretty boring during the flight, because all they do is they just, you know, they have to fly pretty steady, same altitude, and they run everything on autopilot, and then the mission director tells them from time to time, okay, 1 degree further, so they have to turn a little bit so the telescope goes in the right direction. And then they just do that, and then they go and wait again. Okay, here's another picture of the telescope. This is the German contribution to SOFIA. So the telescope was built in Germany. The aircraft was modified in the US and bought by the US. And yeah, and then at some point the telescope was built in. As I said, the bulkhead is the effective carrier, so that connects the telescope to the aircraft. It has a 2.7 meter mirror. 2.5 meter are actually illuminated, so you can, you know, in terms of resolution, spatial resolution, and light collecting power, you can actually say it's a 2.5 meter mirror. The wavelength range is from the optical all the way to the submillimeter regime. And we're talking here about something massive. These are 17 metric tons that are being lifted up into the stratosphere every night. And so it's quite a big thing. So this here should give you another idea of what is in the infrared universe and what we can observe with SOFIA. We can measure molecules like CO, we see dust, we see fine structure lines, things like hydrates, HD, NH3, and PAHs. You may have heard of those as well. They are very famously were observed by ISO at the time, and then of course more by Spitzer, and then of course water, right? And water is this interesting thing that, you know, before ISO, we didn't quite know about water in space, because it's all blocked by the atmosphere, because the atmosphere is full of water. So we didn't really know, and the big news from ISO at the time was that, wow, the universe is full of water. And so, you know, it is one of the products that actually happen when stars form. And well, we didn't know this, and now we do. And so water is one of the interesting constituents that are being studied in space, and they are quite important. So you see here, this is a spectrum. It gives you an idea. This is a you know, a typical extragalactic spectrum. So you have PAHs here, and then you have a dust bump here at the long wavelength range, and you have all these constituents that make spectral lines. And on the right here, we see all the fascinating things we can look at. Below, you have this gives you an idea of the transparency of the Earth atmosphere. So there is a big submillimeter array in South America, in Chile. It's called ALMA. And this black line here that gives you the transparency of the atmosphere at the ALMA site, which is a very dry, very elevated area that should have a good transparency. But even there, down here in the long wavelength range, the atmosphere is completely blocked, while at SOFIA altitudes, we have a reasonable transparency that allows us to make observations. But as you see, even there is still a residual, so it is not perfect, but it is also good enough for science. So look at some science examples. Well, let me start first with this is probably at the moment the greatest discovery that SOFIA has made. That was published last year. It's called helium hydride. And it is, well, if you believe what theory says, when this was the first molecule that actually formed after the Big Bang. And so it's a helium atom and a proton. And well, apart from the fact that this was the first, it gives us a good idea about how the radiation transfer, how the energetics worked out at the beginning of the universe, because well, we know that in order to form stars, the universe had to cool off. And there are various mechanisms that are proposed for this. And the helium hydride here is one way to in the chemistry pathways to build other molecules that can radiate then and cool off the universe. And well, this was quite an interesting thing, because they did not even think they could observe it, because all the calculations said, well, SOFIA is not quite sensitive enough yet for this. Nevertheless, it was still possible to do. I'm going a little bit faster here over things now in the interest of time. So we have a long wavelength broadband camera on board. It's called HAWC+. And in the long wavelengths, we can see particularly the coal dust. And so this is an example where we're looking at actually a gravitationally lensed system. So we are using a foreground galaxy as a giant telescope. So in addition to the telescope that SOFIA carries, there's basically now a giant intergalactic telescope that magnifies a galaxy that is much further away behind it. And but because of that, we can actually see it, and otherwise it would be too faint, and we can tell things like the energetics of that galaxy, which is of course from the very early universe. In this case, the interesting question was, okay, how much AGN contribution was there actually, and how much starburst? And in this case, there was not much AGN, but you know, this is the kind of science you can do with SOFIA. HAWC Plus has an additional and, well, you might say even more interesting quality. It can measure polarization. So polarized light gives you an idea. So the theory is that you have spinning elongated dust particles. They align with a magnetic field and basically spin around the magnetic field lines. And that way you have all these particles with a alignment direction. And that, of course, then as they emit infrared light, they emit effectively polarized light. So this polarization can be measured with SOFIA, and it is quite a unique and clear indicator of a magnetic field this way. There are very, very few other effects that can create this kind of polarization. This is different at other wavelengths. So the far infrared is a very good area to actually get this, to measure this and be reasonably sure that we have actually a magnetic field as the reason for it. So these are all examples here where we have measured polarized light. And the fascinating thing here is that the magnetic field lines are often directed in the direction of the flow of matter. So in this case, M82 has this gigantic outflow here. So basically a stellar wind going into the polar directions. And well, the polarization measurements confirm here that also the magnetic field lines are aligned with that outflow. Interestingly also, if you look at a face-on galaxy, you see that the magnetic field lines are aligned with the spiral arms. And again, that's now, if you, and we've seen this alignment also along the poles in other galaxies. So think about how this magnetic field looks now in 3 dimensions. It's quite intriguing. If we go a little bit closer to home here, this is our own galactic center, which harbors a supermassive black hole. And also this one here was imaged in polarized light. And you, oops, that was not, here we go. So here you see the magnetic field lines. You see a ring around the central region. So this is all matter that we can see in the infrared. We would not be able to see the galactic center at all if not for infrared light, because it is blocked by dust in the foreground in the spiral arms. So yeah, and so what we see here also is magnetic field lines, and some first analysis of that data showed that it may be that this the magnetic field here is actually preventing the black hole in our galaxy from being fed. So not so much matter falls into it. So it does not act like the active galactic nuclei we find in other galaxies that outshine everything else in those galaxies. Okay. A completely different example here, which is also, again, a little bit closer in our galaxy. The GREAT instrument, which is a heterodyne radio receiver, measures at a very high spectral resolution, which also then gives you a very high velocity resolution if you take into account that the Doppler shift moves the frequency of lines back and forth. In this case, The line is the C2 or C plus line, as we call it, at 158 microns. And this was observed with upgrade. This is a specific configuration of the grade instrument. And what it was doing, it was mapping all of this area and basically recording for every image point a whole spectrum. So which includes this line. So this line, the position of the line could be measured very accurately, and you can get a velocity image. And what I'm showing here, this picture, this is basically a 3D data cube where 2 dimensions are the spatial dimensions of the image, and the third is the spectral dimension. And yeah, well, you could now, if you look at it, you could see a dragon, which basically appears right now. So it looks like a dragon, right? Here's a head. And anyway, the interesting thing is also that thanks to SOFIA being, landing every day and being upgradable, we can fly the newest technology. And while this observation could have done already with Herschel if it had enough time, but it was flying only for 4 years. Nowadays, with the newer technology and a few more pixels instead of just 1 on Herschel, we could collect this whole data set in 40 hours, while on Herschel it would have taken 2,000 hours, which would have been a major fraction of the mission. So this also shows a little bit how interesting SOFIA is when it comes to new technology development. Okay. Other possibilities where you can learn about the interstellar medium is with instruments like FIFI-LS. So these are fine structure lines that were measured, I believe, with FIFI. I'm not quite sure actually. Could have also been with GRADE. But the point is, what is interesting for scientists are these photon-dominated regions here. These are the interfaces between ionized radiation in the interstellar medium that comes here from one side, ionizes the medium, and here in the back you still have non-ionized species. So these regions here, this is the interesting part where a lot of science investigation is done. On the right side here, you see then different colors that represent different temperatures. So it's basically, it's warmer on this side and colder on the other side. Here to illustrate that we are also with SOFIA pretty much at the pulse of the time. The recent dimming of Betelgeuse that made quite some headlines because everybody thought, okay, there's a possibility that it could go supernova. We know that it should go supernova within, well, the next 10,000 years, I believe. And well, of course, we thought, okay, this is a possibility. However, it seems that it just has been a short, probably ejection of material that dimmed the visible foreground. In the infrared, there's basically almost no change. So we have immediately organized a observing campaign with 3 instruments. And you see here, this is one example data from EXIS. This is a mid-infrared spectrograph with high resolution. And these spectra here, they are taken in March 2017, and that's the blue one, and in February 2020, when we were in this dimming phase. And in the infrared, there's almost no difference, except for a few things here. For instance, these are the water lines, and maybe you have some difference there. And there's already a paper out about this. Another interesting area is we can even measure the moon, right? And there's the big question of water on the moon. And there's a NASA mission, it's called Viper, that has that wants to land there and look for water. And what we can do with SOFIA, because we have access to this 6.1 micron feature that you can also not see from the ground, we can actually look where the probability for finding water for this mission is highest on the moon. So in particular here, these polar regions are quite interesting, because we think that is a higher probability for water to be there, because the sun, there's a lot of shadow from craters and from mountains, because the sun comes from the side. And so we have a director's discretionary time program here that wants to look for water, and these observations will be scheduled soon. This year is already something that happened quite a while ago in 2015. We did a Pluto occultation. This is something that, again, only SOFIA can do, because we can fly right where the occultation occurs. What happens is a shadow is projected onto Earth, and basically projects. So a star basically illuminates Pluto in this case, and Pluto casts a shadow onto the Earth. And what we can see is the dimming from that passing of Pluto in front of that star. And if you calculate exactly where the shadow goes and fly to the center, and again, only SOFIA can do this properly, then you can see the central flash here at the center, which is effectively the entire atmosphere of the planet lighting up, being illuminated here by the star that is right behind it. Like in this photo here by the New Horizons mission, after it had passed Pluto and flew through its shadow. And this is, of course, then our sun that is here, the illuminating star, while in our case for SOFIA, this is a star quite far away, and which does the illumination here. All right. So we have a number of instruments. I'm going to go quickly through this. We have a visible camera. This is effectively our guider camera, but can also be used for science. It's at visible wavelengths. That's the only instrument we have there at those wavelengths. And it is mounted in parallel to everything else. All the other instruments are being connected to the telescope individually. So you can have only one of them mounted at the time. And here you see basically, so this is forecast. It's a mid-infrared camera, 5 to 40 micron, and it has also a low resolution spectrometer capability. With PECS, this is also mid-infrared, has a much higher spectral resolution, so there you can do some more interesting work in terms of physics. However, resolution always costs sensitivity, so this works only for the brighter objects. Then we have HAWC+. This is a far infrared camera, and it also has a polarimeter, and this generates all these fascinating magnetic field images. FIFI-LS is a spectrometer also for the far infrared. This is a twin to PECS, which flew on Herschel, and so at least the spectrometer section. And this instrument is quite sensitive and also good at extragalactic work. It has only intermediate spectral resolution. That's why it's so sensitive. On the other hand, we have great here. This is the heterodyne receiver, and this instrument has a very high spectral resolution. But again, it is not that sensitive anymore because of the high spectral resolution. In resolving power, so spectral resolving power versus wavelength space, our instrumentation looks like this. So here on the left, we have the CCD camera. It's called FBI Plus. Forecast is our camera that's here. So you have the wavelength coverage here in the mid-infrared. It has GRISM, so that gives it spectroscopic capability. EXIS is the higher resolution spectrometer. That is quite a unique instrument, actually. So that gives you access to this very, very high spectral resolution. GREAT, of course, has even a higher spectral resolution as a heterodyne receiver that covers here certain bands. And FIFI-LS is the other spectrometer with medium resolution. And here's HAWC Plus, that's only a camera and polarimeter, of course. So what I wanted to say, just GREAT is here covering a lot of these areas that are not accessible from the ground. However, this is where the atmosphere already becomes transparent again. So ALMA is covering those atmospheric windows here, and both are actually quite complementary and are meant to be used as such, right? And well, the future, of course, is JWST in the mid-infrared. So this is the telescope that's being built at the moment in the US and hopefully to launch soon. This will cover all this mid-infrared regime. So yeah, you can argue whether we still need forecast. However, EXIS will still outshine even JWST at these very high resolution spectra. So that's something that only can be done with SOFIA. And then there are still unique abilities that SOFIA will have in this region until new missions come along. And those missions are planned at the moment rather for the 2030s, not earlier. So SOFIA is unique. It has access to the mid-infrared, and it can it has a fast turnaround for new instruments. So we can build in a few years. We can build a new instrument, bring it on board, and fly it. This is something that a space mission cannot really do. Space missions take a long time to plan, to build, and then to launch. And what you fly effectively on space missions is rather old technology, because you have to be really, really sure that it works, because you cannot fly up there easily and repair. What was done on Hubble was kind of exceptional. That's not what you normally have the money for in a science mission. It is meant for a 20-year lifetime, and we hope that that is the case. Here you see, in terms of time, there's a little bit of infrared observatory history, if you will. Actually, I'm missing IRAS here, which is even earlier out here. IRAS was the first mapping observatory, but it was not a pointed observatory. ISO was the first that could actually point to a certain place in the sky and then integrate there and make some observations like imaging or even spectroscopy. Then we had Spitzer, Akari, and of course Hubble had an infrared capability too, but only in the near infrared. Then we had Herschel that explored first the really far infrared region. WISE was here, and we had Spitzer, which had this enormously long lifetime, very unusual for an infrared space mission. It was just recently switched off. You see, this is an old slide here. I have to move this further out. JWST is now has been slipped again. That goes further into the future. In the meantime, all of this area here is, we have no space missions, we have no missions, no observatories that can do any of this area here. This is, SOFIA is the only one that can observe there. So how do we observe with SOFIA? there's an annual proposal call. We have a two-phase proposal process, and there's a whole number of constraints, of course. We have only one instrument on the plane. We have to plan flight series. So when you basically keep the instrument on for 2 to 3 weeks, and then you change it to another one. We do service mode observations. So we basically, the observers submit their proposals, they define them, and then we execute them for them. However, observers are welcome to fly with us and make decisions on the fly. And they can then also see how the data was taken and have a very good idea then of any issues that may be relevant for their data reduction. In the end, the data is pipeline processed in the Science Center and made available to the observers in the ERSA archive. We have certain constraints, as you can see. So here you see the window. The telescope is right there behind what you see here. This is the secondary mirror. In the back, that is the primary mirror. So we open this in the stratosphere, and clearly there's a big limitation on the elevation that we can actually observe it. So 23 to 58 degrees of elevation. And you can also imagine that, well, you cannot really turn this telescope in azimuth. So our plane has to fly at a 90-degree angle to what we want to observe. Well, and then, of course, you want to be returning to the originating airport. Usually we fly out of Palmdale in California. That's near Los Angeles, on the other side of the mountain range there in the Mojave Desert. And we fly between 10 hours and 8 hours. And after every flight, we want to come back. That means we need to select our targets in such a way that we fly into the right directions in order to come back at the end of the night. There are also special use areas and military restricted zones. Mexico doesn't let us overfly, and so forth. So lots of constraints there. We want to fly as high as we can. However, because we have a lot of fuel at the beginning, we cannot rise that much. So we typically start at 39,000 feet, and then as we get lighter, we can climb further. So basically, then with all these constraints, we have to optimize the science that we do. And so we do this over a year. We take all the proposals, all the objects that come from the proposals of the observers, then we put them into a computer program and get an idea of where we put the instrument campaigns, where we put things like maintenance phase and so forth. Here you see this is one of the flight patterns that we have. So here on the right, this is Palmdale. Okay, here's the California coast, and we're looking here over much of the Pacific. And so we fly out here and we do so-called flight legs, and each of these flight legs means we're looking at a certain region, at a certain object. In this case, for instance, here we're looking at Mars for calibration. Here, antennae, that means these are the antennae galaxy. The reason why this is a funny arc is because, of course, the Earth is rotating, so we have to follow the object as it moves from our point of view. Here, this is a little bit of a demonstration of how the flight path goes. So here we're looking at one object at the beginning. We're gaining altitude and setting up, and here this is the Mars leg and so forth. And as if you look closely here, while we're doing this, the Earth is rotating slowly, and so we have to take all these constraints into account. Okay, so after we have all the proposals in and deliberated, and we have a time allocation committee that looks at them very carefully and selects the best. Then we make a first high-level schedule for the year, and we try to match all the flight series to our target pool. And then of course, as you know, because of all these constraints, the flight plans are sensitive to the exact dates. So we cannot just move things easily around that have been planned for certain flights. So if we move things around, then the flight plan may change. So we have some latitude by, you know, about a week or two, but then things have to change. And yeah, about 10 weeks before the start of the series, we start with the real flight planning, so the detailed flight planning. About 6 weeks before we have made up our mind usually, and then things are getting observed, and invitation to the observers are sent out. Here's I don't want you to read this, but gives you just an idea of how such a schedule looks. These are all the colored things here are flights of SOFIA. There are different types of flights. For instance, here this blue is when we go to New Zealand, because we want to see the southern sky as well. And it actually turns out that the water vapor in the south is lower than usually in the north. So these are actually for us very precious observing times in the year. We have a data cycle system that the proposers get all their information from in order to do these proposals. There's something called USpot. It's a software that helps astronomers to prepare their proposals. You get all kinds of help, like visualizing how your observation is, where your observation is going to be on the sky, and so forth. And there are time estimation tools online that help you in determining how long you have to observe your object, of which you hopefully know a little bit, some idea about, you know, how bright it will be. So you need to know a little bit about your science object in order to set this up. And important here is the atmosphere. So the atmosphere is, there is still residual atmosphere, so we have to take this into account. And one interesting thing I just wanted to tell you that's quite not necessarily what you expect. The speed of the Earth towards your object or away of it can actually be relevant, because of the Doppler shift, it will move the wavelengths where you observe with respect to the residual atmospheric transmission into bad places or into good places. So it really depends also on when you observe a specific line, whether you will be lucky or not. And you need to put this into your flight planning, because otherwise you end up in a situation like this and you don't see nothing with zero atmospheric transmission. So in the end, when everything is observed, it will be pipeline reduced by our staff experts, and then the data ends up in URSA. This is the infrared database. So that is located at IPEC at Caltech, and they host our data archive. They host data archives for many more missions, like Herschel, like Spitzer, etc. And the nice thing of this database, they have a lot of additional tools where you can then put your data into relation with our data and so forth. So you can do multi-wavelength science immediately. And all the SOFIA data is there. You can access it. Everybody can get to it. You have to have an account, but that's not a problem. And you can basically play with the stuff and try to make sense out of it and do science. And these are just the dates here that are currently envisioned for the next proposal. The current coronavirus situation is, of course, a bit of a problem, and We are probably still sticking to this timeline, but yeah, stay posted. It is not 100% sure whether things will stay as they are. I have here a number of links that are interesting in case you want to stay connected with the project and learn more, follow it. And I think that's yeah, that's all I have about it.
Thank you very much.
Yeah, I don't know, are there questions, or how do you want to proceed?
Well, now are the questions part. Let me also let us thanks to speaker. I encourage everybody use the reactions down there. You put the clapping here also as the in real situation during the real meetings. I will share my screen with the questions, and let's go through them and let's see what people are asking. And what other people are interesting. So, and I encouraging everyone to voting here and putting questions also during this part. So let's see. Okay, we have first question. First question is about, okay, so I will read it. So telescope on SOFIA has a system to compensate vibration and even turbulence. If I will sit on your telescope, I will not feel turbulence during the flight.
If you sit, yes, if you sit on the telescope, okay, we are not letting people do this for starters.
Yeah, sure.
But I believe you will not feel much. That is true.
Yeah, well,
yeah. We have a nice movie. Unfortunately I don't have it here at the moment, but we have a nice movie where we look at the telescope from inside the cabin during a flight, and it's actually a quite bumpy ride. We have some turbulence there. And you see this instrument jerking around, you know, and moving and doing this. But actually, what you have to realize is you are doing the moving. The flight, the airplane is doing the moving. The instrument is rock steady. And let me say this also. So this telescope is quite a marvel, actually. It will hold the position on the sky even under these funny conditions, to basically 1 to 2 arcsecond accuracy. That's quite impressive, is it?
Yes.
Yeah.
Well, it's possible. I mean, why the airplanes, normal airplanes, don't use it? I will fly with them much more. Okay, yeah. So thank you. Another question. What was the longest and highest SOFIA flight? For which observation or experiment they were done?
Okay, I don't have a table with the records, and I apologize. But as I say, the highest SOFIA flight goes up to 14 kilometers. That's the limit, basically. And at that point we already push the engines very hard. And so that's not good for the lifetime either. But basically that's towards the end of the flight where we can really go high. And the duration is limited to 10 hours simply because the pilots have to, they have a certain time they are allowed to work. And we cannot go over that. Otherwise, we have to take a second crew. Normally, we don't do that. SOFIA can fly longer. That's not the problem. The problem is more actually the working times.
So you could fly longer. Just okay. So another question: which one of SOFIA's results, discoveries, articles do you like most, and why?
I must say, at the moment, I'm quite intrigued by this helium hydride publication from last year. This is what I like about it is, you know, it shows how serendipitous sometimes a discovery can be, because, well, these guys, they said, okay, there could be this line, we might be able to see it, but they said, well, yeah, it's probably too faint. And then they did a calculation and it showed that, okay, I think it was too faint by a factor of 4 or so. And, but because the team is actually the team that built the great instrument, they said, well, let's give it a shot anyway. And because they have guaranteed time, they gave it a shot, and let's try the impossible there. And well, they got a result, and actually a correction to all these calculations. So basically some of these parameters were incorrect. So this just shows you, okay, you know, sometimes you also have to try the impossible in order to make progress.
Yeah, and sometimes you get result. So, so if I'm correctly saw it somewhere, one flight cost $1 million. Yes?
No.
No. So how much is cost?
Well, okay, depends how you depends how you calculate this. I think in terms of fuel, it's $100,000 for the fuel. And yes, probably, I mean, okay, again, it depends how you calculate all this. Of course, to have all the maintenance crew, you have the onboard crew, you have the telescope controllers, you have the mission directors, etc., the pilots. They all contribute, and of course, you have to pay them salaries. So yeah, maybe. So again, 1 million is a kind of a wild ballpark number, and I'm not sure how accurate that is, but yeah, again, depending how you calculate.
Yeah. Okay. So next question. So you mentioned Star Trek in presentation. Someone asked, do you like Star Trek? If so, what series you like most?
I like Star Trek a lot. I mean, look, I grew up with it, and I think a lot of scientists that you would ask will probably tell you, oh yeah, Star Trek is something that really inspired me to take this up. And so, you know, I mean, I'm from the generation that grew up with Captain Kirk and so forth. I also know about Next Generation, of course, but that's already a little bit past my time. I didn't follow that so much. But if you ask what other series I like, then there's a series that's called Babylon 5, which aired I think in end of the 90s, and I like that a lot too, because it has another aspect of, you know, different races trying to work it out together, being diplomatic and so forth. And of course, it's a good projection on our real life. I also like it because, you know, my job here has a lot to do sometimes with negotiating between different parties. We have also cultural differences, you know, between the US and Germany. You know, cultures are not the same. And you find this when you work closely together, then you suddenly see, oh yeah, we do things differently. And there's just a different cultural approach how things are done. And I'm sure if we work together on some project, we would also find that, oh yeah, we are used to different things, how we do business, right? And so all of this always needs constant communication and working things out. And you know, that, so in that respect, you know, I find Babylon 5 is quite a fascinating take on the space operas that you have.
I think it's easy to understand. For me, Star Trek is something like science. It's the symbol of the going somewhere where no one has gone before. So it's discovery. So okay, another question. Well, this one is well, how many scientists are involved in SOFIA? Yeah, you are observatory, so you are. But please.
So in terms of, so purely scientists, if you say just, okay, in the Science Operations Center, the scientists there, I would say at the moment in the 20, about 20 to 30 scientists at most. Not all of them have pure scientist jobs, but that's what we have. And then of course we have many more scientists involved who actually make proposals, right? And then who do the data reduction and who write publications from that. So per year, I think this was another question somewhere, per year we get something in the order of 250 proposals roughly. And you know, of those typically only a fraction can actually be observed then. So we have oversubscription factors depending on the German and the American program, but roughly we have oversubscription factors of around 5.
Yeah, I think there is questions about it down here, but well, let's see later. Okay, so here is, does SOFIA have typical routes it takes when flying, or it is a random? I think you mentioned in presentation, but you could address it also. Yeah,
it is of course not random. There are always certain routes you have to take at the beginning because of air traffic control. Remember, these are not. This is an airplane that operates within the normal air traffic pattern. So, and we are not that special. So sometimes we also have to wait for traffic. So the air traffic control sometimes does not let us get higher, although we want to, because there's another airplane. Okay. Then there are all the avoidance zones, so kind of military operation zones and so forth, that we try also to get around. So, and that means we develop certain traffic patterns that we often do. On the other hand, you know, the objects that we observe are all over the sky. So, and because we have these clear constraints on where we have to fly in order to observe something, there's quite some randomness as well.
Yes. Okay, so not random long planning is behind. Okay, fine. Another question. Where's Venus? Venus has strong infrared air glow observed by SOFIA. Could you see with SOFIA also Earth air glow?
Well, we're seeing it all the time.
Yes.
But for us, it's a dirt effect. We want to get rid of it.
Yes.
Yeah, and so.
So you could estimate how much air glow you have there.
It's an interesting question. I certainly have not looked into the matter, but let me put it that way. If somebody is interested in that question, and if they think that they can get some science out of that, they're welcome to contact us and talk about it, and we can, maybe something can be worked out. There may also be information about that in the data that's already in the archive, right? So again, this is, we are open to a lot more than just our narrow-minded astrophysics.
Yeah, thank you. That's very nice. Okay, so that one. Why Mexico does not allow SOFIA flights?
I have wondered myself. I'm now for 2 years on the project, and this is one of the questions I still have, and I have not had time to dive into it. At the beginning, we also couldn't overfly Canada easily. So Canada, meanwhile, is no problem anymore, and it's actually very good to fly up to Canada, because in the north the atmosphere is even colder, so there's less moisture in the atmosphere, and we're doing even better up there. So yeah, I don't know. I think if we talked very insistently to the Mexican government, maybe we could make a deal. But the South, let's put it that way, the South is not that interesting to us because of the increased water vapor, actually.
Yeah. Okay. Thank you. Okay. Now, can be SOFIA aircraft tracked by public flight trackers?
Yes.
For example, by flight radar. Yes.
Yes. It's the call sign of SOFIA is N747.
Mm-hmm. So there is transponder. We can okay. We could see it. So okay. So here it's another one. Well, about future. To build a next generation SOFIA, what will help more? To have the bigger airplane, so we could have a bigger telescope, or have airplane which could operate higher?
That's a tricky one. First of all, there are not many bigger airplanes that would be that actually would allow to have a telescope built in like what we've done. At the moment, we believe that the 747 solution that we have is probably the best one for an airplane. If you take one of these big Airbuses or so, it would even be more expensive, and cost of flying is already a major expense for us, and also some of the criticism that we have received. So that is probably not the best way. A bigger telescope is certainly a good thing, but I personally believe if we could operate higher, that would be my first priority. And I mean, it depends, of course, on how much bigger you could make a telescope. But let's say if somebody asked me, okay, instead of your 2.5 meter telescope, if we give you a 3.5 meter telescope on an airplane, but operate at the same altitude, or alternatively, you can fly 10,000 feet higher. I think I would take the 10,000 feet higher option with SOFIA.
Because less of the vapor?
Less water vapor, less trouble calibrating the data. Yeah.
Okay. Interesting.
The quality of the data suffers from the atmosphere. This is clear.
And what was the cost of the SOFIA? I mean, budget to build it?
To build it, this again is a very rough estimate I can give you now, but it's close to $1 billion, I think, for the modification and the telescope and so forth. However, this is still cheaper than Herschel, for instance, right?
Yeah. Still cheaper than
here's the thing: when we have operated for 20 years and paid for the fuel and the operations and so forth, at the end of those 20 years, then we will probably also have a similar cost like one of the big space missions, like Herschel or so. However, then we would also have accumulated a similar amount of observing time.
And how much was Herschel?
Herschel was 2 billion, or even more than, a little bit more than that maybe. And that had this had a 3.5 meter telescope, but was only operating for 4 years because of the cryogen was depleted at some point. And I mean, the big advantage that we see in a facility like SOFIA is that we can land, we can modify, we can change the instrument, we can fix it and build new ones. So we have the potential of always being at the cutting edge of detector technology and instrumentation, which a mission like Herschel or Spitzer or so could never do, because you cannot repair them.
You could not upgrade it up there.
Yeah.
Okay, thank you. You probably, next question. You probably do many public presentations for SOFIA. Is there a question from the audience which you remember as special because it was, for example, funny?
I have to tell you, the presentations that I typically give are to a very serious audience of scientists. So they typically want to know, okay, how can I observe, where can I observe? So I have to admit, I don't recall any particularly funny comment right now. But you know, the folks just, you know, they are very interested in just, you know, how do I write a proposal, and how do I get observing time?
Yeah.
It's a very serious crowd.
So let's hope that such question will be in this 11 questions which is in front of us. So next one is, what was the most challenging part of SOFIA observatory technology? What was the most hard to develop, to build?
Well, I guess it's the telescope. I mean, you know, keeping something, well, first of all, building something and integrating this into the aircraft in such a way that the structure is not compromised is very challenging. So I think, I mean, overall, the modification of the aircraft took a long time, because what they did then was, so once they had the telescope in, and they had closed up with the door, they needed to do a lot of, well, already before, but then as well, they needed to do a lot of test flights in order to step by step widen the operational envelope again. So, you know, the first time they opened the door, this was a very critical moment, because you know, you don't quite know whether all your calculations and so forth work out. They had also a lot of wind canal experience before that. Right, and then the other challenge, of course, is the vibration stability of the telescope. We are still, to this very day, we're working on it. There are still some systems that were put into the telescope that are, to this very day, not fully activated, because we do this step by step, and we need to be very sure that everything works. And you know, you don't want to be surprised at 14 kilometers altitude.
Yeah. Yeah. So pretty big door. You have pretty big door. So how many proposals do you get for SOFIA observations per year? How many of them are selected? How many of them are from the USA, Germany, and other countries? Yeah,
so I think I said that before. Something in the order of 250 proposals are received, and we have a oversubscription of roughly a factor of 5 or so. So you can make up the math. So yes,
other countries.
Okay, and then the science return is proportional to what the countries contribute. So the US is contributing 80%, so they also get 80% of the observing time, and Germany gets 20%.
So there is no part for the other countries, like, I don't know, someone from the England cannot apply.
Oh yes, there is. So this is I mean, so the arrangement with Germany is so that's the 20%. So there is a 20% share basically that goes to German affiliated researchers. So you don't need to have German nationality. You just need to be affiliated with a German institute. So you have to work at a Max Planck Institute, for instance, or at a university in Germany also. Then you can apply for the German part. If you are from another country than Germany, then you apply for the US part. The US part is open to any country, right? So if you have a bright idea, you write a proposal, you will, all you have to fill out is, what country, which institute, and so forth, and it will automatically be assigned to the right queue. In this case, it would be US queue then, and of course you have to, well, the US queue is the one that is more competitive. So this is where you get oversubscription factors of over 5 even.
Yeah, so here is another question which is connected to this one. In history of SOFIA operation, did you have any observation proposed by Slovak or Czech institute?
I should have checked this before. I didn't. I don't know. Probably. I don't know. I mean,
yeah. Okay.
We have proposals from all over the world. Yes. Of course, there's quite an overwhelming majority from US institutions that propose.
Yeah.
And so it is hard to compete against them. But I would not be surprised if there was somebody.
Yeah, okay. So another question. Have you ever experienced any problematic flight? Has ever been SOFIA flight necessarily moved to another day because of weather?
Oh, all the time,
Oh,
unfortunately. Yes.
And problematic
so
flight?
Yeah, there are all kinds of issues with weather. We are, unfortunately, a lot of our flights get wiped out because of weather. So here's one of the things that, so first of all, turbulence is something that you don't really want, right? You don't want to be in a wildly shaking airplane and trying to do observations. First of all, there are limits to what the vibration compensation can do. And second, the safety of the people on board is one of our prime concerns, really. And so if the forecast is severe turbulence or so, we will not fly. The other thing is rain. That is not so much an issue in Palmdale, but is regularly an issue in New Zealand. So in New Zealand, we have only 3 airports where SOFIA can actually land in terms of length of the runway and so forth. And when we go, so when we have scheduled a flight, then we have to check whether there is rain forecast for our airport where we want to land again for the time of landing. And if that is so, then we have to check whether the other 2 airports have a forecast too. And actually, we are not allowed to take off if that remains the case. And the problem is not that we cannot land in rain. That's not a problem. But there is the possibility of a door failure. So if we, for some reason, cannot close our door anymore while we are in the stratosphere, then we would have to land in rain. And yeah, our telescope and the instrumentation in the cavity behind the door would not take that lightly.
So what will happen then?
Yeah, we have already tried to relax these rules a little bit, because the probability of the door being stuck is actually very, very low, and at the same time having rain. But so far, NASA rules prevent us from doing that. So we're actually losing a number of flights also because of that.
Oh, yes. Yeah. How look your typical working day? What consumes most of your time?
Email. Well, I think, okay. My day specifically is determined by a lot of meetings. So I have to talk to a lot of people. We have to, just work things out. So this is, at the director level, most of your time is really spent communicating and talking to people, trying to get a picture of what is really going on, and based on that, take certain decisions, or trying to convince other people of certain decisions they, in your opinion, should take. Yeah. So, and part of this communication business is, of course, email, right? So I have, I get a lot of email. I spend a lot of time on answering that, or do whatever is necessary in order to react to it. So not so much of my time is anymore spent on crunching numbers and getting into the thick of it. Although I still like to do that, but that it gets less and less.
Yeah. Yeah. Okay. That's that is nice, I think. If you could have a budget like James Webb Space Telescope, so approximately $10 billion, what space mission or experiment you will like to see to become reality?
Yes, please give me that.
So good question.
Yeah, that's a fascinating question. So if I stick to my profession here, okay. I mean, there are experiments on in development. So effective successors to SOFIA. One is called the SPICA. That's a European Japanese mission. That's so basically ESA and Japan are working on that and trying to get that approved. This is for 2030, I think launch date 2032 or something like that. Mm-hmm. This is a cool telescope in the infrared, pretty big, and that would be a next quantum leap in terms of sensitivity and what we could do in infrared. It's a space mission, right? And then there's even a bigger one that's a US proposed Origins called mission, even a bigger mirror, and that would probably be able to fly mid-2030s. Both are currently under being proposed, and yeah. Now, I hope that at least one of them goes forward, and that will probably require funds. Well, not as expensive as 10 billion, but these are substantial investments. Now, if you're asking me what I really would like to do as kind of, you know, for my personal interest, and if I just had
dream, yes,
could spend it like this, I would be interested in an interferometry mission. So something where we could peek in the infrared into active galactic nuclei. That's where I would be very interested. I would really like to know, okay, how does this really look in the center of these galaxies? There's a lot of dust that is kind of complicating our picture. We don't really know how these areas look. There are all these theories about a torus of dust around the black hole, and there's an accretion disk, and there's a jet, and so forth. So we have these sketchy ideas, but when we really try to match now the actual observations to these ideas, then things don't fully work out. And so there's still a lot of questions about how this really looks. There is probably very complicated cloud formations, or who knows what. You know, and an interferometer would be an interesting way to shed some light on that. So that would be my, and that would actually then take probably funds of that order. Yeah, there was a US planned mission that was already even in development. It was called TPF, and another one was called SIM. These were interferometer missions. They were actually made in order to rather look at exoplanets, but of course you can do AGN as well.
Yeah. Okay, thank you. Well, historical question: which project or experiment from space exploration history do you like most?
Yeah, I think there was a small Mars mission called Pathfinder, and you know, it was planned as one of these faster, cheaper, better missions with not a terribly high probability of success. And then this little mini rover, I mean, nowadays the rovers are much bigger, but this thing was just, you know, it was just a small little model car that drove around Mars suddenly and gave us all these fascinating pictures. To me, this was just still an amazing idea, and also the technology they used. You know, they blew up a bubble around that thing for landing. So first, I mean, it had, of course, retro rockets, and it had a parachute, but then for the last descent, they just blew up a big air bubble around it and let it bounce off the surface. That was just an unbelievable idea.
Nice.
Yeah.
Nice. Okay, another question. Is there any similar observatory like SOFIA in preparation in the world? Are there plans to build the successor of SOFIA in the next years or decades?
Yeah. So if you ask me, is there another airplane observatory being proposed or built? No. SOFIA is the last of its kind as it appears at the moment. This is also why I make a point of really trying to preserve this. We keep having threats of cancellation of the observatory because allegedly it costs so much money. On the other hand, well, it does cost a lot of money. That's true, but this is a completely unique capability. There's no space mission at the moment until the 2030s, as I said, that will be able to do anything similar. And so for science, for all the science that needs data from that wavelength regime, it's absolutely crucial that SOFIA keeps flying. The only other way you can get currently data in the far infrared is from balloons. Balloon missions have the advantage that they also can go higher than SOFIA, but you need very dedicated experiments on there. So you have a gondola, you have a telescope. This is all, again, a wobbly thing, and it has to be much lighter than the 17 tons of telescope that we fly. So that means it also has a lot of limitations in terms of accuracy and so forth. And the other thing is when a balloon mission that flies typically only for a few days or a few weeks, when that comes down, survival probability of the hardware is about 50%. So, you know, you typically can recover your data if you find it. I mean, there was this example of the the blast mission. So there was a balloon mission over the South Pole. They came down and they failed to cut off the parachute upon landing. So, you know, when it's landed, then you cut off the parachute, but that didn't work. So the whole gondola got dragged for about 200 kilometers across the South Pole and disintegrated on the way. And they were so incredibly lucky to find the hard drive in the end that stored the data. They actually found it, but it's amazing that they did that. So anyway, so balloon missions are the other possibility. And there are some ideas around of also building so-called high-pressure balloons, you know, that can stay for much longer than just a week or two. And that's being explored. I have also looked into airship possibilities, you know, where you can carry a big telescope robotically into the stratosphere, something like that. There are ideas, but nothing firm. The only firm examples are what I said earlier: Spica and Origins.
So you really unique. Will be.
We are, yes.
Yes. Okay, here is interesting science management question. You have the experience to work and lead complex large projects. What is your recommendation? What is the best way to build a productive science team project? Or project? I know this is for long, but well.
For a team to be successful, communication is the one most important aspect. People need to know what they are doing. People need to be well connected. So to me, communication is the very first thing. And then, of course, everything that goes with it. So communication between team members is fostered by, well, human dynamics, if you will. So psychology, really, you know, how well does a team fit together? What are the different personalities? They, you know, a team usually is composed of different personalities, and the mix is what matters there. And of course, there are no, you know, there are no standard recipes really for doing this. In the end, your feel will determine, and a lot of other boundary conditions will determine what team you have in the end. But if you can choose, and if you have some freedom in choosing, then you're aiming for a diverse team with different personalities that kind of complement each other. And yeah, and then you have to feel like one team. So you have to make sure people don't separate too much into groups that kind of start competing against each other, because that's usually also not good. Friendly competition is a good thing, but then you have you don't want to have this overdone.
Yes.
I don't know. This was a large ramble now, and I have probably a lot of more ideas about
this
it.
This is for longer, I think, explanation, much longer. So okay, let's skip to next question. We have last 3 questions. So looking to list of SOFIA publications, there are 100 of them previous year. So I assume that it's impossible to read them all. How much of SOFIA articles do you read?
Yeah, I agree. It's not possible to read them all. In particular, you cannot read them all in detail. So what I typically do is I look at the abstracts, and if I find something particularly interesting, then I drill down. But in practice, I don't get to read more than, say 20% or something of that order. And I should read more, but I personally don't get to do more of that.
Yeah, thank you.
But I get at least I get, there are other folks that read a lot more, that have the time to do this, and then I get a lowdown of the most important ones.
Yeah, thank you. So this one was already answered, but people vote for it. So maybe, well, how many hours one flight takes? Where it is taking off and landing locations?
So the standard flight duration is 10 hours that we use. About an hour at the beginning is used to gain altitude, get to our operating altitude, set up the telescope, and get operational. Then we observe for about 6 hours, and the last hour is then to descend again and land. So out of a 10-hour flight, we get something like 8, sorry, not 6 hours. We get 8 hours of science time out of it. Now there's another flight pattern that we have investigated and that we're using from time to time. That is an 8-hour flight pattern where we get only 6 hours of science time out. So we have the same dead times at the beginning, at the end. The advantage of those is, although they are not as efficient as the 10-hour flights in terms of time, but they give us a higher starting altitude because we don't need to take that much fuel with us. And so we are lighter from the start, and that way we can rather start at 40,000 feet than 39 or 38,000 feet. And that can be an advantage, and it depends on the science we're doing and the, whether we need a particularly good atmospheric transparency for our observations.
Okay, last one. How much miles fly SOFIA so far?
Oh boy. I would have to go back to you on that one. But I guess we, Okay, I could turn this around for your students.
Okay.
So the data cycle system of SOFIA, which you can all access, all you need is sign up. There's no restriction on getting a user account. There's flight data in the database that you can retrieve. So you can in principle find out when, how many flights were done since first light, and you can probably easily make a first guess of,
Yeah, anybody can count.
Yeah.
Yeah. Okay. Okay. So those were all questions. So thank you very much again.
Okay. Well. Okay. You were cut off.
Thank you by clapping there. Sorry.
You were cut off. I didn't hear.
Ah, okay, because my mobile was ringing and I just stopped it for a second. Okay, so thank you again. We are switching now to the short part in Slovak where we introduce next speech. So thank you again, and we really appreciate your talk. Okay.
Thank you very much. Bye bye.
Bye bye. Okay, so let me